Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 45, Synchronous Counters with Parallel Load of Chapter 7, Counters and Registers of the course Digital Logic Design or Digital Systems or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in Digital Logic Design, however there are many books available. In this lecture, we will cover actually synchronous binary counters with parallel load, and also we'll talk about modular integrated circuit counters. Synchronous counters with parallel load. Counters used in digital systems sometimes require a parallel load capability for transferring an initial binary number prior to the count operation. There are 2 methods to add parallel load capability to the synchronous counter: asynchronous parallel load and synchronous parallel load, and we will talk about both. Asynchronous parallel load is achieved by activating the preset and the clear of the flip-flops, because the preset and the clear, both of them are asynchronous inputs. The input load control X is equals to 1 causes a transfer of data from data input line, which is II, into the flip-flop. While when X is 0, the network operates as a counter, and the clock pulses cause the state of the flip-flops to change according to the count sequence. So X is 1, we will load the data, and X is 0 will be a normal counter. So to do this, we will use the preset and the clear. And the truth table for the preset and the clear is quite simple. Okay, the figure gives the truth table and derivation of the active low clear CR and the active low preset PR of any flip-flop. It also shows the network of a single stage of any counter with asynchronous parallel load. Asynchronous parallel load is flip-flop independent, that is, it can be used with any flip-flop equipped with asynchronous preset and clear, as long as they are active low. When they are active low. Now, if the load is 0, we need this to operate as a normal counter. So when X is 0, 0, whether the input is 0 or 1, the preset and the clear will be 1, 1, and 1, 1. It means they will be inactive. Okay? Well, if the load is 1, okay, now I am loading the data. Now to load the data, if I have 0, if the data is 0, I need to activate the clear or CR. Because CR, when it is active 0, the output Q will be 0 instantly, independent on any clock. While when the input is 1, I will activate the preset. When the preset is 0, the output Q will be 1 instantly. So I will move the 1 to Q. I will set the flip-flop. So in this simple truth table, we can find the value of the preset and the value of the clear. So the preset, as you see here, it is XII prime, because if you simplify for the 0, you get XII prime. And this is the preset. So it is a simple NAND gate. If X and II take it to a NAND gate, and this is give me the preset. While the clear, it's XII prime, all prime, which is with simple manipulation will be the preset NAND X, NAND X. So if you take the preset NAND X to the clear, okay, which will be from here, from the table. I mean, this is equivalent to this with simple Boolean algebra. You can work it out as an assignment. So here, when we have 1, 1, we'll have the preset 0 and the clear is 1. 1, 0, we'll have the preset 1 and the clear is 0. And we establish a very simple 2 NAND gate network with the preset and the clear to upload any data that we need from II. So to do this, we can have the design We designed a modular 8 counter with asynchronous parallel load. So a previous counter has already been designed using D-type flip-flop for Mod 8 synchronous counter. And we proved those logical equations. Okay, we proved those in a previous lecture. So if you go to the lecture Design with D flip-flops, you will find this circuit. So here we added to this circuit a parallel input data line, which is I0, I1, I2, okay, and this will allow me to load the data with 2 NAND gates for each of those. X goes along with all. So if X is 0, the network will operate as a normal counter. If X is 1, the network will operate according to this flip-flop as a load function to load the input numbers of data to the counter. Okay, now let's look at synchronous parallel load. The synchronous parallel load is designed by modifying the flip-flop input equation such as the input load X when equal to 1 disables the count sequence and causes transfer of data to the flip-flops. Okay, and we can do this by a simple, for instance, in the D-type flip-flop, we have D1, D2, D3. So the modified with the load, DI load, will be the old DI X prime or IIX. So if X is 0, this will allow me, will be a 0, will be 1, and DI load will be equal to DI, okay, and this will go away. So will operate that a normal counter. Again, if X is 0, this term will cancel out because 0 and II will be 0. And in DI and 1 or 0 will be DI. So this will cancel out and will be equal to DI. However, when X is 1, this will be 0 DI, so this will cancel out and I will have II and 1, so DI load will be II. So after the next pulse, II will be load to DI, II will be load to DI, will load to DI. It means will load to flip-flop I, and the Q output will be equal to II. Where DI load is the ith D flip-flop input with parallel load. DI is the D flip-flop input derived from the next state map. II is the data input, and X is the input load control. So this Boolean function, this logical function, is very simple logic used here with a control signal X. X is 0, I have a normal counter. X is 1, I am uploading data synchronously to the counter. So with 1 clock pulse, all the data will be loaded synchronously to the counter. So if we go actually to a normal counter, and you will implement the equation. So this is the old counter with old, for example, we had A prime BC, okay, NAND X prime. This came from this equation. AB prime NAND X prime, AC NAND X prime, and we added a new term which is XIA, which is the input IA, XIB, okay, so we ended an XIC. So those will give me basically DA, DB, and DC for synchronous parallel load counter. Okay. By using this simple equation, this simple logic, okay, so any DI, regardless what DI is, you will end it with X prime. So every product term in DI will be ended with X prime, and this is what we see here. Those product terms ended with X prime. Well, we use here the Morgan theorem, 2 complements to convert the AND OR to all NAND. This is what we did. Okay, so the AND OR converted to all NAND. Okay, and this is the last term, which is XIA. This is the term which is XIA, IIX, IIX, not XIA. Okay. With this, actually, we are done with the synchronous parallel load and asynchronous parallel load to any counter of our choice. So parallel load is extremely useful in many applications. Now, the next slide talks about modular counters. Integrated, most popular MSI modular counters are the 7492A is asynchronous mode 12 counter, which consists of two subcounters divide by 2 and divide by 6. It has a common clear. The 74160 is a synchronous decade counter with synchronous load, asynchronous clear, enable, and ripple carryout. The 74163 is a 4-bit synchronous counter with synchronous load, synchronous clear, enable, and carryout. The 74176 is an asynchronous decade divide by 10 counter with two subcounters divide by 2 and divide by 10. It has common clear and an asynchronous load. The 74177 is a 4-bit divide by 16 asynchronous counter with two subcounters divide by 2 and divide by 8. It has a common clear and asynchronous load. The 74191 is a 4-bit synchronous up-down counter with asynchronous load, enable maximum output, and ripple carryout. The 74293 is a 4-bit divide by 16 asynchronous counter with two subcounters divide by 2 and divide by 8. It has a common clear. So as you see, many integrated circuits, they have really asynchronous load, not synchronous load, because the design is quite simple. When we have the 74163 has a synchronous load and synchronous clear, enable, and carry out. So there are a variety of counters available, okay, for use if you need them. Okay. I will thank you very much for listening. Please subscribe by clicking on the blue circle. And hopefully to see you soon in the next lecture. Sincerely, Dr. Hassan.